This is a little video talking about the Big Bang. So we're going to talk about what it is and when it happened, but then also a bit about a couple of bits of evidence for the Big Bang. So the Big Bang happened 13.8 billion years ago. So that's how old our universe is. The Big Bang was the birth of our universe. Now, what do we mean by the birth of our universe? It's a bit of a hard one to think about. But basically, as far as we know, what this is, it's the start of time. So it doesn't really make any sense to talk about what's before the Big Bang. As far to the best of our understanding, this was the start of time. It was the start of space. So there was no space before the Big Bang. The universe began with this event. So it's the start of time and space. Now, this picture here basically illustrates the entire history of the universe. So Big Bang, over here on the left, started, and then we can see the picture represents the rapid growth of our universe from that event. So early on, the colours are sort of there to represent a bit about the temperature. So in the beginning, everything was very small, very close together, but also very, very hot. So atoms, as we know them now, with a nucleus and electrons buzzing around them, did not exist. Everything was a big sort of mass of what we call quarks, which are particles which make up protons and neutrons. And as it expanded, it cooled down. So as it got past a certain point, 1 second after the Big Bang, we get nucleosynthesis. That's when the universe has grown enough and cooled down enough such that we can get the formation of nuclei and atoms and things like that. It's not until about 1 billion years in, such that everything's grown big enough and everything's cooled down enough, that we can get gravitation pulling matter together to form stars and galaxies and that sort of thing. So obviously this x-axis here is not quite to scale. And on the far side here, we've got our modern universe as we know it now. Okay, so this is just another little picture to sort of illustrate the same sort of thing, really. On the x-axis, we've got the time since the Big Bang. And on the y-axis, we've got the temperature. So basically, this is showing something similar. Early on, right in the beginning, we've got a temperature of 10 to the power of 31. So 1 followed by 31 zeros. Degrees Kelvin. So hugely hot. So what happened? It started off very, very small and very, very hot. And then as it got bigger, it started to cool down until where we are today, over on the right-hand side. Okay, so what evidence do we have for the Big Bang happening? We can talk about the birth of the universe, but we have some evidence which is how our current theory came into existence. So let's talk about a couple of pieces. Okay, the first one is something called cosmic microwave background radiation. So what is this? Well, and this is sometimes shortened to CMB. So when the Big Bang happened, we mentioned before that everything was hugely dense and hugely hot. So basically what that means is we had a lot of energy around. So let's say this is still fairly early on in the universe. What I'm going to do here is represent some photons. So these are just little waves of light, which, because it's very hot, everything's giving out a lot of energy. Okay, so what I'm going to do is I'm going to simulate what happens as our universe grows. Take a look in particular at what happens to the light. Okay, so hopefully we could see that these photons get stretched out. So as the universe expands, that light gets stretched. As it gets stretched to longer wavelengths. So this is basically what cosmic microwave background radiation is. It's the light and electromagnetic waves from when the universe was created, which as the universe has grown and grown and grown, these waves have been stretched out and stretched out and stretched out, such that they have become microwaves, cosmic microwave background. And we can detect these. So if we take a little look at this picture here, if I have a microwave telescope, I can look at the sky. And just as normally we look into the sky with a visible telescope and get certain pictures of stars and moons and planets and all that sort of thing, I can use a microwave telescope and I get a completely different picture. And it looks a bit like this. Now, it doesn't look like much, but we can see little patches of high-density microwaves and low-density microwaves, and this is basically a snapshot of how the light has developed since the universe was born. So this picture here is evidence for the Big Bang. Well, on the right-hand side, if you ever go into your grandparents' house back in the day, you might have seen an old cathode ray analog TV that looks a bit like this, one of the ones with the big backs. And if you ever switch these analog TVs on when there's poor signal, you get this staticky background noise. So what that is basically, that white noise is electromagnetic radiation being picked up by your TV antenna. So that is also a snapshot of the beginning of the universe. Okay, so I'm just going to remind us a bit about the electromagnetic spectrum song. I'm sure you can see it for yourself. So here, we got a snapshot of the electromagnetic spectrum. So early on, we had very high energy. So over here, we've got very short wavelength. So over in the gamma part of the spectrum. As my universe grows, these waves get stretched out such that now they are in the microwave part of the spectrum. So they've been stretched out so much over the 13.8 billion years that they've now got a wavelength of about 1 millimeter. So that's about here. So cosmic microwave background has a wavelength of approximately 1 millimeter and an effective temperature of 2.7 Kelvin. So what's the significance of that 2.7 Kelvin? Well, that is basically what we think of as the temperature of deep space. So temperature, we know, is a measure of the average kinetic energy of molecules, is how we normally think of temperature. In space, when it's a near vacuum, that definition makes much less sense. But we can define the temperature of space as the temperature of the radiation all around us. So 2.7 Kelvin, 2.7 degrees above absolute zero. So that's the first piece of evidence. The second piece of evidence is something called redshift. So redshift is very similar to Doppler shift, which we've talked about before. So this little picture here is an illustration of Doppler shift. So what do we normally associate Doppler shift with? Well, it's sound. So if we think about what Doppler shift with sound is, it's when something is making a noise and it moves past you. So I've got a couple of examples here. So that's Doppler shift with a car horn. As it's coming towards you, listen to the pitch. It's very high pitched. As it's coming towards you, as it's going away from you, that pitch drops and it sounds deeper. Here's another one. So, let's think about those examples for a second now. When it's coming towards you, what happens? Well, we've got a shorter wavelength. All these waves here get squashed together. And so if it's a sound wave, if those peaks get squashed closer together, we perceive that as a higher frequency. When it's moving away, we get the opposite effect occurring. So those waves get stretched out, they have a lower frequency, and they sound at a lower pitch. One more for you, Doppler shift with sound. Okay. Now, we can take that exact same Doppler shift model and apply it to light. So things need to be moving much faster because light travels much faster than sound, but we get the exact same things occurring. Now take a little look at this picture on the right. This is basically illustrating the exact same thing. As something is approaching, we get a shorter wavelength and a higher frequency. Well, what does that mean? In terms of light, well, the higher frequency part of the visible spectrum is violet. But more commonly we call it blue shifted. So I'm going to write it there. So light, if something's moving towards you and emitting light, light from that source will be shifted towards the blue end of the spectrum. So it will look slightly bluer than it would if it wasn't moving. On the other side, well, if it's moving away, we get the exact opposite effect occurring. We get a longer wavelength, we get a lower frequency, and we get something called red shift occurring. So light from an object which is moving away from you at a very high speed will appear redder than if it wasn't moving. So how does this fit into the Big Bang and our theories of the universe? Well, let's have a little think about what's going to happen as my universe expands. So here's my universe in the beginning. And I'm just going to draw a few planets on here. So this is us. Oops. This is us here on Earth. That's my Earth. And that's us standing on the Earth, looking out into space. Then we've got a couple of planets near us in the universe. Okay, so this is a very simple diagram illustrating us looking out into space. Okay, so what I'm going to do now is I'm going to see what happens as my universe gets bigger. Okay, so what we're interested in is what's happening to the distance between us, the observer, and the galaxies which are further away. So this distance here is initially very small. As the universe gets bigger, these galaxies appear to be moving away. Now let's compare the close galaxies to the further away galaxies. Well, this guy here will look like it's moving away much faster. Appear to move away much faster. So this is significant. So what this basically means, if I look at a closer galaxy and it's moving away, it will be a little bit redshifted. But if I look at a galaxy that's a long way away, it will appear much more redshifted than the closer galaxy because of the expansion of the universe, it will be moving away much quicker. So this is another piece of evidence for the Big Bang. So, what do we actually see when we look at these galaxies? Because we know that stars all have different colours and due to their temperature and things like that. So how do we know what the original temperature was? The original colour was. Take a little look at this picture here. Now, when I look at a galaxy, I see these different bands which have been taken out. So this is what we call an absorption spectrum. So basically, when I look at certain elements, they have characteristic wavelengths of light which they absorb really strongly. So hydrogen, for example, or helium, will have characteristic values for which they absorb the light. So, and we can test this and we'll come up with certain numbers. So over here we might have something like, I'm making these numbers up, 650 nanometers, 610, 615, and so on, going down towards the other end, which would be about 400 nanometers. So this would be characteristic of a certain element. It's like an elemental fingerprint. Now, why this is useful is if I look at a distant star and I see this spectrum, I know that star might have something like helium in it. I can identify the components of that star from looking at the light being given off by it. The other reason this is very useful is because of this redshift effect. Because these bands are very characteristic, if I have those same bands but shifted over by a little bit, I know that that star has been red shifted or blue shifted. So take a little look at this second row now. These exact same bands will have been shifted over a bit. So this 650 band on the far right has been moved over by a certain amount. So there's going to be a difference in the wavelength there. So let's say that 650 nanometer band is now at 652 nanometers. My 615 nanometer band might now be at 617 nanometers. My 610 nanometer band might now be at 612 nanometers. So all these bands have been shifted over towards the red end of the spectrum. So what does that mean? Well, that means if it's red shifted, it's moving away. The converse of that is if something's moving towards us, it gets blue shifted. So all those bands will be shifted to the left-hand side of the spectrum a little bit. So as a bit of a reminder, blue light, or violet light, has a wavelength of approximately 400 nanometers. Red light has a wavelength of approximately 700 nanometers. So they'll get shifted to one end of the spectrum or the other depending on which way they're moving. Okay, so why this is significant is when we look at distant galaxies, when we look at distant galaxies, they appear redshifted. Now, what does this mean? The significance of this is that they're moving away from us. And how does that link into the Big Bang? Well, this means that the universe is expanding. Okay, so that is redshift. Now, the last little bit we need to talk about is we can quantify redshift. We can come up with an equation which describes it mathematically. So that's this equation here. So this equation basically describes the amount of redshift given how fast something is moving away. So let's take a little look. I'm going to start with this bit in the middle here. So, lambda naught, so lambda, if we remember, so lambda is our notation for wavelength in meters. Lambda naught is the original wavelength. So if that star wasn't moving away, what would the wavelength of that light be? So delta wavelength means change in wavelength. So by how much has this been shifted? So in the previous example, the one we had here, we were going from 650 to 652. my change in wavelength is 2 nanometers. So if I look at this bit here, how can we find change in wavelength? Well, I could find this one here would be the observed wavelength. So we might have, in the case before, we had 652 minus the original would equal 650 nanometers. Okay, on the right-hand side of the equation, what have we got? Well, V is something called recession velocity. So basically, what that means is, how fast is it moving away? And that will be measured, as with most velocities, in meters per second. And lastly, C is the normal symbol for the speed of light. If you remember Einstein's famous equation, E equals mc squared, the C in that equation stands for the speed of light. So what is the value for that? Well, that has a constant. The speed of light in the universe always remains the same, and that speed is, I'll do it in a different colour because this is an important number, 3 times 10 to the power of 8 meters per second. So it's worth keeping that number in the back of your mind. Really important for some of these calculations we're going to do now. So this is our equation which describes redshift mathematically. So to finish up, I was just going to give you a bit of practice at having a go at putting this equation into an exam-style question. So pause the video now if you want to have a little go at this one. Okay. So, question 1. When looking at a nearby galaxy Galileo, light from a spectral band of 450 nanometers is redshifted by 3 nanometers. So, 1 part I. What is the wavelength of the band that is detected on Earth? So, if we remember our electromagnetic spectrum, we said that violet is 400 nanometers, while red is 700 nanometers. So if this started off at 450 nanometers and it's redshifted, means that band is shifted towards the red end of the spectrum, that means we're going to add 3 nanometers, which will give us 453 nanometers. So, we know that that galaxy is moving away from us. If, on the other hand, it was blue shifted, we would have to subtract 3 nanometers. At this point here, it's worth just reminding ourselves what that prefix nano means. So nano is a billionth, or in standard form, that means times 10 to the power of minus 9. So 453 nanometers equals 453 times 10 to the minus 9 meters. Okay, part 2 of that question. What is the recession speed of Galileo? Well, that's when we need to use our equation there. So we've got our equation here. Delta lambda over original lambda equals V over C. Well, let's start plugging in some numbers and trying to work this one out. Well, what is my change in wavelength? Well, we already know that it's been redshifted by 3 nanometers. I'm going to write that in standard form here. Divided by my original wavelength. So that is the light that was given out by the star, which here is 450 nanometers. This is equal to my recession speed, which is what I'm looking for, divided by the the speed of light. And we remember from before, that equals 3 times 10 to the 8 meters per second. So now we've got a little equation here which we can solve. We've got 10 to the minus 9 on both sides here, so I can cancel those. And I should end up with 3 over 450 times 3 times 10 to the 8 equals my recession speed, which in this case will be 2 million meters per second. So that's how fast this galaxy is moving away from us. Bit of standard form, 2 times 10 to the 6 meters per second. Okay, question 2 here. Andromeda is our nearest galaxy. Light from a star in Andromeda is blue shifted. What does this mean? Well, basically, we just need to understand what red and blue shift means in terms of the motion of the galaxy. If it's blue shifted, that means that the star is moving towards us. Okay, thank you for listening, guys.